Welcome to this walkthrough. In today's session, we will be exploring a solution to LeetCode problem number 1919. While the specific problem details are unavailable, we will analyze potential approaches and strategies that can be applied to similar challenges. Let's dive in and break it down step by step. LeetCode problem number 1919, titled LeetCode problem information unavailable, currently lacks detailed information on the LeetCode platform. Without access to the problem statement, input-output formats, or constraints, we are unable to provide an accurate problem description or examples. If you are encountering this issue, it might be due to a restricted problem or a temporary unavailability. Please check the LeetCode website for updates or clarification regarding this problem. When tackling any algorithmic problem, it's essential to consider various approaches to identify the most suitable solution. One common starting point is the brute force approach. This method involves systematically exploring all possible combinations or states to reach the solution. While this is often the most intuitive and straightforward way to begin, it tends to be computationally expensive. For instance, if you're searching for a specific subset or evaluating every potential combination, nested loops or recursion can enumerate all possibilities. However, the trade-off is that brute force solutions often scale poorly, with complexities like O(2 to the power of n) for subsets or O(n squared) for pairwise comparisons, making them impractical for larger inputs. To address these inefficiencies, we then consider optimized approaches using data structures. Choosing the right data structure, such as hash maps, heaps, or segment trees, can significantly improve performance. For example, hash maps allow constant-time lookups, which is ideal for problems with frequent searches. Similarly, segment trees or Fenwick trees can handle dynamic range queries efficiently, reducing operations to logarithmic time. These tools are invaluable for improving both the speed and scalability of solutions. Now, while optimized data structures can improve runtime efficiency, they often come with trade-offs, such as increased memory usage and implementation complexity. Another powerful class of strategies includes divide and conquer and dynamic programming. These methods work by breaking the problem into smaller subproblems. Divide and conquer solves these subproblems independently, often combining their solutions later, while dynamic programming takes a more iterative approach, storing intermediate results to avoid redundant calculations. For example, if you're tasked with finding the maximum or minimum value in a sequence, dynamic programming can efficiently store and reuse results, as seen in problems like the maximum subarray sum. These approaches often achieve polynomial time complexities, such as O(n log n) or O(n squared), depending on the problem. Another method to consider is greedy algorithms, which focus on making locally optimal decisions at each step with the goal of reaching a global optimum. These are especially effective for problems like interval scheduling or constructing minimum spanning trees. However, greedy methods rely on the problem having the greedy choice property to guarantee correctness. While these approaches are computationally efficient, often running in O(n log n) or O(n), they require careful analysis to ensure they solve the problem correctly. Here, we've chosen to focus on the optimized approach using data structures. Even without specific details of problem number 1919, this strategy is a versatile and practical choice for a broad range of algorithmic challenges. The intuition behind this approach is that many problems involve optimizing operations over arrays, strings, or graphs. By leveraging data structures like hash maps, heaps, or segment trees, we can significantly reduce time complexity for common operations such as searching, updating, or querying. Brute force solutions, while easier to implement, are rarely efficient enough for competitive programming or larger inputs. On the other hand, while divide and conquer or dynamic programming can be powerful, they may introduce unnecessary complexity for problems where data structures alone can offer an efficient solution. The decision to use optimized data structures strikes a balance between runtime performance and implementation complexity, making it a robust strategy for solving optimization-focused problems often encountered on platforms like LeetCode. However, it's important to acknowledge the trade-offs of this approach. While optimized data structures can drastically improve performance, they may introduce additional space overhead, which could be a limitation in memory-constrained environments. If the problem involves deep recursion, overlapping subproblems, or scenarios where intermediate results need to be reused extensively, dynamic programming or divide and conquer might offer a more effective solution. Ultimately, even though the details of problem number 1919 are unavailable, leveraging optimized data structures provides a flexible and efficient framework for tackling a wide variety of algorithmic challenges. This approach aligns well with common patterns seen in competitive programming, offering a balance between efficiency and practicality that makes it a dependable choice for solving complex problems. To tackle any algorithmic problem effectively, the first step is to thoroughly understand its requirements. This means identifying the input format, such as whether it's an array, string, or graph, and determining the exact output expected, like an integer, boolean, or a modified data structure. It's equally important to clarify any constraints and consider edge cases, such as handling empty inputs or large values. For example, in a problem where we need to find the maximum sum subarray, we should define how subarrays are generated and how their sums are calculated. This foundational understanding sets the stage for developing a reliable solution. Now that we understand the problem requirements, the next step is to classify the problem into a known category. Problems can often be grouped into areas such as array or matrix manipulation, dynamic programming, graph theory, or mathematics and combinatorics. For instance, if the input involves a graph, we might consider traversal methods like BFS or DFS for connectivity or shortest path algorithms for weighted graphs. Once the category is clear, we start with a brute force approach. This means writing a simple, exhaustive solution that guarantees correctness. While this solution may not be efficient, it helps us analyze time complexity and identify bottlenecks. For example, in a problem requiring all pairs of elements, nested loops can be used to evaluate all combinations, even if it's not optimal. With a brute force solution in place, the next step is optimization. This involves using data structures that reduce redundant computations, such as hash maps for fast lookups, heaps for priority-based processing, or union-find structures for managing connected components. Algorithmic techniques like reducing nested loops into single-pass iterations, applying caching or memoization, or converting recursive solutions to iterative ones can also improve efficiency. For example, instead of using a brute force two-loop approach to calculate sums, we can use a prefix sum array to achieve linear time complexity. Finally, we must ensure that edge cases are handled properly, such as testing minimum and maximum input sizes in special scenarios like uniform data or no valid solutions. Once the optimized solution is implemented, it's crucial to validate it. Start by dry running the algorithm with small test cases to verify correctness, comparing the outputs to expected results, especially for edge cases. Additionally, analyze the algorithm's time and space complexity to ensure it meets efficiency requirements. Some key strategies include divide and conquer, where problems are broken into smaller subproblems, pre-processing methods like using prefix sums for range queries, and even greedy algorithms when they can guarantee optimal solutions. For problems with overlapping subproblems, dynamic programming is particularly effective, as it allows you to iteratively build the solution by clearly defining states and subproblems. Data structures play a pivotal role in implementing efficient algorithms. Arrays and lists are fundamental for indexing and sequential data storage, while hash maps allow constant time lookups and frequency counting. Stacks and queues help manage data in LIFO or FIFO order, and heaps enable dynamic priority-based operations. For more complex relationships, graphs can be represented using adjacency lists or matrices. To illustrate, consider the problem of finding the maximum sum subarray. A brute force approach would evaluate all possible subarrays, leading to cubic time complexity. However, an optimized method like Cadon's algorithm simplifies this by maintaining a running sum, resetting it to 0 if it becomes negative, and tracking the maximum sum encountered so far, bringing the complexity down to linear time. To summarize, we can outline a final algorithm template to systematically address any problem. Start by parsing and validating the input. Then, implement a brute force solution to establish a baseline and analyze its complexity. Next, optimize the solution using techniques like sliding windows or dynamic programming. Thorough testing, including edge cases such as empty inputs, all negative numbers, or single elements, is critical to ensure robustness. Conclude by analyzing the algorithm's time and space complexity. For example, Cadon's algorithm, used for the maximum sum subarray problem, has a time complexity of O(n) in all cases since it processes each element once, and it uses only O(1) auxiliary space for its variables. This systematic approach ensures both correctness and efficiency. Here, we are working with a Python implementation of a generic LeetCode style problem. While the problem details for number 1919 are unavailable, this template demonstrates a solution for calculating the sum of all unique elements in a list. First, we define a class called solution and implement a method named solve that takes a list of numbers, nums, as input. The process begins by creating a frequency dictionary to count how many times each number appears in the list. This is achieved using a loop where we use the get method to increment the count for each number, or initialize it to 1 if the number is encountered for the first time. Next, we initialize a variable called unique_sum to keep track of the total sum of unique elements. After that, we iterate through the frequency dictionary and check if any number appears exactly once. If it does, we add it to unique_sum. Finally, the method returns this calculated sum, which represents the total of all unique elements in the input list. Now, we see an example of how to use the solution class and its solve method. We create an instance of the solution class and pass a sample input list 4, 5, 6, 7, 4, 5 to the solve method. The method processes this input to calculate the sum of unique elements. In this case, the numbers 6 and 7 appear only once in the list, so they are identified as unique. Their sum, 13, is returned as the output. Finally, we print the result to verify the output, which matches the expected value. This example demonstrates how the logic in the solve method effectively identifies and sums up unique elements in a given list. Here, we start by importing the necessary libraries and defining our main class, solution. Inside the class, we have a method solve that takes an array of integers as input. The goal of this method is to calculate the sum of elements that appear only once in the array. First, we create a frequency map using a hash map. This map will store each number as a key and the count of its occurrences as the value. To populate this map, we iterate through the input array and use the getOrDefault method to handle cases where the key doesn't already exist. Next, we initialize a variable, uniqueSum, to 0. This will be used to store the cumulative sum of elements that are unique. We then loop through the entries in the frequency map. For each entry, we check if the count, or value, is equal to 1. If it is, we add the corresponding key, which represents the unique number, to our sum. Finally, the method returns the value of uniqueSum, which represents the sum of all unique elements in the array. In the main method, we create an instance of the solution class and define an example input array 4, 5, 6, 7, 4, 5. This array contains some duplicate numbers, like 4 and 5, as well as unique numbers, like 6 and 7. We then call the solve method with the example input and store the result in the variable result. To display the output, we use system.out.println, which prints the result to the console. Based on the logic in the solve method, the expected output here is 13. This is because the numbers 6 and 7 are the only ones that appear exactly once in the array, and their sum is 13. This example demonstrates how the implementation works to identify and sum the unique elements in a given input array. To start, we are given the input array 4, 5, 6, 7, 4, 5, and our goal is to calculate the sum of unique elements, meaning elements that appear exactly once in the array. First, we build a frequency dictionary to count how many times each number occurs. Initially, the dictionary is empty, and as we iterate through the array, we update it. Adding 4 gives us 4, 1, then adding 5 updates it to 4, 1, 5, 1. Continuing this process, we add 6 and then 7, resulting in 4, 1, 5, 1, 6, 1, 7, 1. When we encounter 4 again, we increment its count to 4, 2, 5, 1, 6, 1, 7, 1, and similarly, when we encounter 5 again, the dictionary becomes 4, 2, 5, 2, 6, 1, 7, 1. Now that we have the frequency dictionary, we can identify elements that appear only once. We initialize unique_sum as 0, then iterate through the dictionary. 4 and 5 are skipped since they appear more than once. 6, which appears once, is added to unique_sum, making it 6. Adding 7, which also appears once, updates unique_sum to 13. With the final sum of unique elements calculated as 13, we return this as the output for the first example. Now, let's look at another input, 1, 2, 2, 3, 1, 4. As before, we begin by creating a frequency dictionary. Initially empty, we add 1, resulting in 1, 1, then add 2, updating it to 1, 1, 2, 1. When we encounter 2 again, we increment its count to 1, 1, 2, 2. Next, we add 3, giving 1, 1, 2, 2, 3, 1, and when we encounter 1 again, we increment its count to 1, 2, 2, 2, 3, 1. Finally, adding 4 results in 1, 2, 2, 2, 3, 1, 4, 1. To identify unique elements, we initialize unique_sum as 0 and iterate through the frequency dictionary. Both 1 and 2 appear more than once, so we skip them. 3, which appears once, is added to unique_sum, making it 3. Similarly, 4 is added, resulting in a final unique_sum of 7. Returning the output for the second example, we get unique_sum equals 7. Now, let's examine the third input, 10, 20, 30, 40. Here, all elements are unique, so the frequency dictionary will count each number as appearing exactly once. We start with an empty dictionary and add 10, resulting in 10, 1, then add 20, updating it to 10, 1, 20, 1. Adding 30 gives 10, 1, 20, 1, 30, 1, and finally, adding 40 results in 10, 1, 20, 1, 30, 1, 40, 1. To calculate the sum of unique elements, we initialize unique_sum as 0 and iterate through the frequency dictionary. Since all elements appear once, we add each to unique_sum. Adding 10 gives 10, then 20 updates it to 30, 30 updates it to 60, and finally, adding 40 gives a total unique_sum of 100. This value, 100, is returned as the output for the third example. In analyzing the time complexity of our solution, we begin by looking at the process of building the frequency dictionary. Here, we iterate through the nums list, which has a size of n. For each element, we perform a constant time operation to update our dictionary using the frequency.get, number, 0, plus 1 method. This results in a total time complexity of O(n) for this step. Next, we consider the iteration through the frequency dictionary itself. The frequency.items method gives us an iterable of key-value pairs, and since the dictionary size is proportional to the number of unique elements k in nums, we are iterating over k items. For each of these pairs, we perform quick, constant time operations such as checking a condition or performing an addition. This step contributes k to the overall time complexity. In the worst-case scenario, where all elements in nums are unique, k could equal n. Combining these steps gives us a total time complexity of n plus k, which simplifies to n. When we simplify n plus k to n, it's because the number of unique elements k is always less than or equal to the total number of elements n. Now, let's assess the space complexity of the solution. The primary contributor to space usage is the frequency dictionary, which stores up to k unique elements where k is the number of distinct elements in nums. Since each dictionary entry uses constant space, the total space required for the dictionary is k. Additionally, we use a few scalar variables like unique_sum and loop counters, which require negligible space, or O(1). In the worst-case scenario, where every element in nums is unique, k equals n, and thus the space complexity is k, which simplifies to n. This gives us a space complexity that scales linearly with the size of the input. To gain further insight, let's compare this optimized approach with a brute force method. In a naive solution, you would need to check the frequency of each element in nums using nested loops, leading to a time complexity of n squared. This is because, for each element, you would iterate through the entire list to count its occurrences. In contrast, our optimized approach leverages a dictionary to store frequencies, allowing us to calculate the solution in linear time, or n. This significant improvement is achieved by traversing the list only once and processing the dictionary in k. Now, considering the best, average, and worst-case scenarios, in the best case, if the input list is empty, no iterations are performed, and the time complexity is 1. For the average case, where elements are distributed randomly, the time complexity remains n. Even in the worst case, where all elements are unique, the time complexity still holds at n, demonstrating the efficiency of this approach. To solidify our understanding, let's break down the reasoning behind the big O notation mathematically. The dominant term in the time complexity arises from the single traversal of the nums list, which contributes O, n. Adding to this, we have constant time operations for dictionary insertion and a linear iteration over k unique elements, resulting in a total time complexity of O, n plus k. Since k is always less than or equal to n, this simplifies to O, n. On the space complexity side, the dictionary is the primary factor, as it stores up to k unique elements. This results in a space complexity of O, k, which again simplifies to O, n, in the worst case where k equals n. Both time and space complexities are linear, ensuring that this solution is both time efficient and memory efficient for large inputs. When solving problems, one common pitfall is not accounting for edge cases. These include scenarios like empty arrays, single-element inputs, or inputs that hit maximum constraints. Neglecting these can lead to runtime errors or incorrect outputs. For instance, in problems involving subarrays, you might forget to handle cases where the array has only one element or when the subarray spans the entire array. Another frequent issue is relying on inefficient brute force approaches. While they might be easy to implement, their time complexity can become unmanageable for large inputs. For example, in combinatorial problems, generating all possible subsets or permutations without optimizing can lead to exponential complexity like O, 2 to the power of n, which is impractical. Finally, a misunderstanding of the problem statement can derail your solution entirely. If you skip over key constraints or nuances, you may implement logic that doesn't align with the problem's requirements. For example, a problem might ask for distinct combinations, but if you don't account for this, you might end up counting duplicates. These mistakes can be avoided through careful reading, planning, and testing. Off-by-one errors are another frequent difficulty, especially in problems involving loops, ranges, or indices. These occur when you misinterpret whether an index is inclusive or exclusive, leading to out-of-bound errors or incorrect logic. For example, when iterating up to n, accessing ARR n would go out of bounds. Another trap is overcomplicating your solution. While it's tempting to design elaborate logic, many problems have simpler, more elegant solutions. For instance, using a complex data structure when a simple array or hash map would suffice can waste both time and effort. To improve your problem-solving approach, focus on recognizing common patterns. Techniques like sliding windows, prefix sums, dynamic programming, and binary search appear frequently and can significantly streamline your solutions. Additionally, understanding space-time trade-offs is critical. For example, using a hash map might increase space usage but drastically reduce time complexity for lookups. In interviews, remember that explaining your thought process is just as important as the solution itself. Clearly articulate your reasoning, how you handle edge cases, and your complexity analysis. Start with a naive solution, then refine it iteratively. Interviewers value this problem-solving progression. Many problems you encounter are variations of well-known classics. For example, toSum, LeetCode number 1, uses hash maps to optimize performance, while subarray sum equals k, LeetCode number 560, leverages prefix sums for efficiency. Combination sum 2, LeetCode number 40, focuses on generating unique combinations under specific constraints, and longest substring without repeating characters. LeetCode number 3 showcases sliding window techniques for optimizing string traversal. When tackling these or similar problems, it's important to consider alternative approaches. Brute force solutions are often the simplest to write but fail to scale due to high time complexity. Their trade-off is ease of implementation versus practicality for larger inputs. Optimized iterative solutions, on the other hand, often use auxiliary data structures like hash maps or arrays to improve time complexity. These strike a balance between space and time efficiency but can be harder to implement. Another approach is divide and conquer, which breaks the problem into smaller subproblems, solves them recursively, and combines the results. While it's ideal for recursive patterns, it may require additional memory for the recursion stack. Dynamic programming is another powerful approach for solving problems that involve overlapping subproblems. It works by breaking the problem into smaller, manageable components and storing intermediate results to avoid redundant calculations. This makes it particularly efficient for scenarios with repetitive subproblems. However, the key to using dynamic programming effectively is defining the state carefully and ensuring that the transitions between states are optimized. While it can significantly reduce time complexity, it often comes at the cost of increased memory usage to store intermediate results. Understanding these trade-offs and applying dynamic programming judiciously can help you solve even the most complex problems efficiently. Thank you for following along. Today, we explored general strategies for solving LeetCode problem number 1919 in the absence of specific details. Remember, the key to mastering coding challenges is consistent practice and breaking down problems into manageable steps. See you next time for more tips and solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!